SwayamPrabha. Digital India. Educated India.
Welcome to lecture 32 of the course on multivariate data mining, methods and applications. The title of this lecture is Clustering Based Upon Mixture Models. Now, so far we have discussed several clustering methods in previous lectures. In all those clustering methods, we don't assume any distribution about the population from which we get observations, or we don't assume any probability model for the observations. In mixture based clustering, we assume that the observations are coming from a mixture of distribution. So, the observations have different clusters because the observations are generated by a mixture of different distributions or mixture of the same distribution with different parameters. So, one can make use of this phenomena for obtaining the clusters. So, if we assume a mixture of distribution for the observations, then for estimating the parameters or for obtaining the clusters, the cluster to which a particular observation belongs, we make use of EM algorithm. So, in this lecture, I am going to discuss the cluster analysis based upon the mixture of distributions, and we will also discuss the EM algorithm for obtaining the clusters as well as for estimating the parameters of the mixture distribution. Now, here we have plotted a mixture of three normal densities, say 0.3 into normal distribution with mean -7, variance 4, plus 0.4 into normal 1, 4, plus 0.3 into normal 8, 4. And we have 10,000 observations, and then ultimately we plotted the density. So, from this mixture of normal distributions, we have generated 10,000 observations first, and then we have plotted the probability density of the observations, and from here you observe that the observations show some kind of clustering. Say some of the observations are from this particular distribution, some of the observations are from this particular distribution, and some observations are from this particular distribution. So, your observations may show clustering behavior. The observation may belong to three different clusters. Now, this is the histogram of a random sample of size 10,000 from a mixture of normal distributions. So, basically you have random bimodal sample. So, again it appears that the observations are from two different clusters. Now, this kind of phenomena gives us one more option for clustering. We assume some distribution, some mixture of distribution for the observations, and then using that mixture model, we may go for clustering. So, in clustering based upon mixture models, we are creating clustering methods based upon a statistical model, which is a mixture model with stochastic elements. Then traditional statistical inference frameworks could be applied. We can make use of say method of maximum likelihood, or traditional statistical testing procedures also can be used. Often for obtaining the maximum likelihood estimators or for clustering purpose, we make use of expectation maximization or EM algorithm for missing data. So, first we discuss EM algorithm for the missing data. Now, suppose X follows a probability distribution P dot given psi. Here psi is unknown parameter vector. So, the complete likelihood function is, we denote it by L psi given x, which is equal to Px given psi. Now, suppose some components of x are missing, and then we write x equal to say x observed transpose x missing transpose whole transpose. So, x is the observation vector from this probability distribution P, but it has two parts or two kinds of observations. Some of the observations are known, or you have taken some of the observations which are included in this vector, and then some of the observations are missing also. So, x observed is the observed part of x and x missing is the missing part of x. It has two parts. Then basically your objective is to estimate psi. Not only psi, you are also interested in estimating this missing part, x missing. So, you want to estimate x missing and psi both. Now, suppose the probability that a particular variable is unobserved, it depends only upon x observed and not on x missing. So, we make this assumption. A particular variable is missing or unobserved, the probability of this event depends upon just x observed, and this probability does not involve x missing. Then the observed data likelihood is say L observed psi given x observed is equal to, we integrate this joint probability distribution of x observed and x missing over x missing, so that we get the marginal probability distribution of x observed given psi. Then the maximum likelihood estimator of psi based upon x observed is say psi hat equal to what we do. This is the likelihood function for the observed data. So, we maximize this likelihood function. with respect to psi. So, the maximum likelihood estimator is argument maximum over psi L observed psi over given x observed. So, this is the likelihood function just on the basis of observed data. Then we maximize it with respect to psi, and then we find the value of psi for which this is maximum, and that value gives you the maximum likelihood estimator just based upon the observed x's. Now, directly obtaining psi hat usually fails. So, one can go for EM algorithm. EM algorithm is a two-step iterative procedure. It has two steps. One is E step and the second step is M step. In E step, we compute the conditional expectation of log likelihood given the observed data x observed. And in M step, we update the parameter estimate by maximizing the conditional expectation from the E step. So, these are the two steps of EM algorithm, expectation maximization algorithm. So, now we consider the EM algorithm. The input is say initial guess of parameter vector psi, say psi hat naught. So, first we initialize the parameter vector. You have some initial guess for the parameter vector psi, then you can use that initial guess. And suppose that value is psi hat naught. Then we write x equal to x observed transpose, x missing transpose, whole transpose. So, basically x is equal to x observed and x missing. Then for m equal to 0, 1, 2, so on, iterate between the following EM steps. Say E step, we compute q psi given psi hat m. We have psi hat m at the mth step, and q psi given psi hat m is equal to expectation of L psi given x observed psi hat m, and we compute q as a function of psi. And then we come to m step. We find psi hat m plus 1, which is argument maximum over psi q psi given psi hat m. And then ultimately we stop when we achieve the convergence of log likelihood. Here this small l psi given x denotes the log likelihood. Now, we can write the probability density function of p x missing given x observed psi as p x missing x observed given psi divided by p x observed given psi. It is just like writing the conditional probability density function of x given y as the ratio of joint probability density function of x, y divided by the marginal probability density function of y. So, this is the conditional probability density function of x missing given x observed. This is the joint probability density function of x missing and x observed, and in the denominator you have the marginal probability density function of x observed. Or you can write p x observed given psi is equal to p x missing x observed given psi divided by p x missing given x observed psi. So, we just take the denominator here and this part here. So, we come to this expression. Now, we take log of both sides. So, here we get log of p x observed given psi, and we denote it by small l. So, small l psi given x observed is equal to log of p x observed given psi. Then on the right hand side we get log of p x missing x observed given psi, and x missing x observed may be written as x. So, log of p x given psi or small l psi given x minus log of x missing given x observed psi. Now, this part of the likelihood or log likelihood is due to the missing data. Now, this is the complete log likelihood. This is the log likelihood based on the observed data, and this part is due to missing data or part of L psi given x due to the missing data. Now, we take expectation of L psi given x observed, which is equal to log of p x observed given psi with respect to the conditional density p x missing given x observed psi dash. Now, notice that in this conditional density x observed is given. So, expectation of the left hand side remains the same. On the left hand side we get L psi given x observed, and on the right hand side we get q psi given psi dash minus h psi given psi dash, where q psi given psi dash is equal to the integral of L psi given x, and then we multiply it by the conditional density of x missing given x observed and psi dash, and we integrate it with respect to x missing. Or this is equal to expectation of small l psi given x observed psi dash. Similarly, h psi given psi dash is the integral of log p x missing given x observed psi, and then we multiply it by the conditional density, and then we integrate over x missing, which is equal to expectation of log Px missing given x observed psi, and then given x observed psi dash. Now we write x missing equal to Px missing given x observed psi divided by Px missing given x observed psi dash. So this ratio is H. Then we make use of this result. Log x is less than or equal to x minus 1. And we obtain H psi given psi dash minus H psi dash given psi dash equal to expectation of log H x missing given x observed psi dash. You just substitute the values of H psi given psi dash and H psi dash given psi dash here, and then you write this ratio equal to H x missing. So ultimately you get this log H x missing here. Just make use of this expression for H from here. And then we also make use of this result. So this is less than or equal to expectation of H x missing given x observed psi dash minus 1. And then this quantity is equal to 0, because expectation of H x missing given psi dash is equal to 1. See from here, for given psi dash, the expectation of this quantity is equal to 1. Now this implies that H psi given psi dash is less than or equal to H psi dash given psi dash. This quantity is less than or equal to 0, or H psi given psi dash is less than or equal to H psi dash given psi dash. Now utilizing the result that L psi given x observed is equal to Q psi given psi dash minus H psi given psi dash, we have L psi m plus 1 given x observed minus L psi m given x observed, and then we write the values of these two expressions here in terms of Q and H. So we get Q psi m plus 1 given psi m minus H psi m plus 1 given psi m minus Q psi m given psi m plus H psi m given psi m. Now this is greater than or equal to Q psi m plus 1 given psi m minus Q psi m given psi m, because this quantity is always greater than or equal to 0. So thus EM algorithm obtains psi m plus 1 to make Q psi m plus 1 given psi m greater than Q psi m given psi m. So with each iteration, the log likelihood increases, and then ultimately under some mild conditions it converges. Now we consider EM algorithm for finite mixture. Suppose the observations are from capital K classes and pi small k denotes the kth class. for all k equal to 1 to capital K. Now, you have to divide the data by class, and then you have also to estimate the parameters of each component density of the class separately. So, you have to do both. You have to estimate the parameters, and remember that we are assuming a finite mixture of densities. So, different components have different densities. You have to estimate parameters of different components, and then you have to divide the data by class also, or you have to estimate the class of data also. Now, suppose we introduce a k vector of dummy variables. Say xi missing equal to xi1 missing, xi2 missing, so on, xik missing, where xi small k missing takes value 1 if xi observed belongs to pi k and it takes value 0 otherwise. So, basically your missing observations are these indicator functions taking value 1 if the ith observation belongs to pi k and it takes value 0 otherwise. Now, we augment the ith observation xi observed to produce a complete data vector. We augment the observed value with the missing value. So, we write xi equal to xi observed transpose xi missing transpose whole transpose for all I equal to 1 to n. So, what we have done? We have converted the mixture of distribution problem to missing data problem. Now, suppose xi missing or IID multinomial distribution from k classes multinomial 1 pi, where pi is equal to pi 1, pi 2, pi k. So, xi missing are IID following multinomial with single drop. Then xi observed given xi missing follows, say, product k equal to 1 to capital K f k xi observed given theta k to the power xik missing. Notice that xik missing takes value 1 if the observation belongs to class k and it takes value 0 otherwise. Then complete data log likelihood is you take log of the likelihood function and we denote it by small l psi given x. So, this is equal to small l theta k pi k xik missing given x. These are the parameters of the mixture of distributions. These are the probabilities associated with different classes or probabilities of the multinomial distribution, and these are the missing data. And then we write it equal to summation I equal to 1 to n, summation k equal to 1 to k. You get xik missing here because you are taking log of the likelihood function. So, you get xik missing and then log of pi k f k xi observed given theta k. So, this is the complete data log likelihood, this one. Now, we come to the E step. In each step, we compute Q psi given psi hat m by replacing x I k missing in L psi given x by say x hat I k missing psi hat, which is equal to expectation of x I k missing given x I observed and psi hat m. So, psi hat m is the estimator of psi or estimator of the parameters obtained at the mth step, or you can say psi hat m is the current value of psi. Then at the mth iteration, x I k missing is estimated by the posterior probability that x I k missing belongs to pi k. So, this is how we estimate x I k missing. We estimate this posterior probability, and we estimate this posterior probability by say pi hat k m. This is the probability of a particular class at the mth step. We multiply it by f k x I observed given theta hat k m. So, this is the current value of theta k, or the current estimator of theta k, divided by the summation over j pi hat j m f j x I observed given theta hat j m. So, this is an estimator of the missing observation at the mth iteration. Then we come to the m step. We have obtained x I k missing at the mth step. Then we insert x I k missing in the log likelihood L psi given x by the probabilities of class membership provided by the E step. E step provides you the probabilities of class membership, these probabilities. So, we insert the same values in L psi given x. Then update the parameter values from the E step by maximizing L psi given x with respect to pi k theta k. So, now we have these missing values or estimators of missing values from the E step, and then we substitute these missing values in the log likelihood. We maximize it with respect to pi k and theta k. Then the m step for updating mixture proportions pi k is given by say pi k m plus 1 is equal to 1 upon n summation I equal to 1 to n x I k missing m. We take average of all x I k missing m. So, this is pi k m plus 1 for all k equal to 1 to capital K. Now, we iterate these two steps, the E step and the M step, until we achieve convergence of the log likelihood. And once we achieve the convergence, we get the estimators of missing values as well as the class probabilities. Then ML determination of the class of the ith observation is the class corresponding to the largest value of x hat I k missing. Once you obtain all these x hat I k missing for k equal to 1 to capital K, then you classify the ith observation in the class which has maximum probability or maximum value of x hat ik missing. Now, we consider this example of mixture of two univariate Gaussian densities, say phi x given theta 1 and phi x given theta 2. So, both are normal densities. Theta 1 is equal to mu 1 sigma 1 square and theta 2 is equal to mu 2 sigma 2 square. So, these are the parameter values. Pi 1 is equal to 1 minus pi and pi 2 is equal to pi. So, these are the mixture proportions. And then, just for convenience, we drop the subscript k. Then, in each step, xi missing m is equal to pi hat m, and then we multiply it by the density phi xi observed given theta 2 hat m. Now, we have these estimators. Theta 2 hat m means mu 2 hat m sigma hat square m divided by 1 minus pi hat m phi xi observed given theta 1 hat m plus pi hat m phi xi observed given theta 2 hat m. So, this is the E step in which we find xi missing m, provided these thetas and pi's are already available from the m step. Here pi hat m is equal to 1 upon n summation over I xi missing m. Then we maximize the log likelihood L theta k pi k xi k missing given x, and the log likelihood is summation over I equal to 1 to n, k equal to 1 to 2. You have just two classes, xi k missing log phi k xi observed given theta k. And then we fix xi k missing m equal to x hat I k missing m. Then in the m step, we get the estimates, say mu 1 hat m plus 1 is equal to summation I equal to 1 to n 1 minus xi missing hat m xi observed divided by summation I equal to 1 to n 1 minus xi missing hat m. Now, notice that in the usual case, when you have a single normal distribution, then the maximum likelihood estimator of mu is simply the sample mean. But here it is the weighted mean, and then these are the weights. Further, mu 2 hat m plus 1 is equal to summation over I xi missing m xi observed divided by summation over I xi hat missing m. Then sigma hat 1 square m plus 1 is equal to summation I equal to 1 to n 1 minus x hat I missing m xi observed minus mu 1 hat m plus 1 square. This is already available from this step. And then we divide it by the sum of 1 minus x hat I missing m. And similarly, we obtain the estimator for sigma 2 square at the mth step. This is the estimator. So, this is how you can employ EM algorithm for obtaining the estimator of mixture of two univariate normal distributions. Then possible model selection procedures for selecting number of clusters and or cluster models. So, you have to decide the number of clusters as well as a proper probability distribution for the clusters or a proper cluster model. You can make use of log likelihood ratio test statistic or some information theoretic approaches, like you can make use of AIC or BIC. You may also consider Bayes factor for selecting the number of clusters or cluster models, or we can make use of Markov chain Monte Carlo methods using reversible jump MCMC or birth and death process methodology. Of course, I am not going into the details of all these procedures like Bayes factor or the procedure based on MCMC. Or you can make use of non-parametric bootstrap assessment of the number of modes in the data using a kernel density estimator. Again, I am not going into the details of this procedure. Then, how many components K? Suppose lambda K is the likelihood ratio for comparing a mixture having K components with a mixture having K plus 1 components. You consider two mixtures, one with K components and one with K plus 1 components, and then you take the likelihood ratio. Then this is the likelihood ratio test statistic minus 2 log lambda K, and this statistic follows a chi-square distribution with degrees of freedom equal to the difference in the number of parameters in the two cases. You have two cases, one with K components, another one with K plus 1 components. So, we can make use of this likelihood ratio for selecting between K and K plus 1. Then we repeat the test for a succession of increasing values of K. And ultimately, testing stops the first time when a K mixture density is not rejected in favor of a K plus 1 mixture density. Usually, this test actually overestimates the value of K. Here I have taken an example of the Spinney data set, which consists of 75 points in 4 groups. And then we have plotted this data set here. We have used the Gaussian mixture model for identifying the clusters. And for selecting the number of clusters, we have used BIC, the Bayesian information criterion, as well as ICL, integrated completed likelihood criterion. And then this is the summary of the data. We have mean, median, etc. Actually, we have scaled the data, so obviously the means are 0 and variances are 1. Then this is the BIC, this is ICL. And in fact, we have taken 5 clusters. And this is the clustering table. In first cluster, you have 23 observations, second one has 14 observations, and so on. The last cluster has just 3 observations in it. So, first we have fitted the Gaussian finite mixture model with the 5 clusters or mixture of 5 components. Then we rerun the program with 4 clusters. Then we obtain these values of log likelihood, BIC and ICL. So, the values of BIC and ICL further decrease. And now, this is the clustering table. This is the plot of 4 clusters using the mixture of 4 Gaussian components. So, in this lecture, we have discussed the clustering based upon mixture models. In this approach, we assume that the observations are coming from a mixture of distributions. And then our problem is to estimate the parameters of different components as well as the class of each observation, to which cluster a particular observation belongs. Since we are assuming a distribution of the population from where we are getting the observation, we may use some statistical procedures. The classical statistical procedures like the method of maximum likelihood estimator, etc. But for obtaining the maximum likelihood estimators for the class probabilities as well as the parameters of different components, we cannot make use of some simple direct procedure. So, we make use of EM algorithm. Basically, the EM algorithm is developed to handle missing data problem, but we can make use of EM algorithm for estimating the mixture of models also. So, we have also discussed some criterion for determining the number of classes or the number of components of the mixture of distribution. So, I am going to stop here. Thank you.
Hello, I am A.K. Sharma and I teach sociology in IIT Kanpur. I am going to discuss a question which is frequently posed to sociologists, and that is, what is the role of sociology in policy making? Now, so far in our country and also in the world, in World Bank, in UN organizations, in Population Council, planning is seen as something for which economists are particularly trained. And very few sociologists were found in planning process. Planning was given to statisticians and to economists. But now gradually planners and states are realizing that sociologists have a very important contribution to make to planning process. What can sociologists do to planning? Sociologists can pose problems. Sociology can identify uh, which problems of society need priority or greater intervention. Like Indian society may be suffering from thousands of problems, but since solution of problem requires expenditure of resources in terms of time, money and manpower, all the problems cannot be solved, or we cannot focus on all the problems. Do you know that our national health plan focuses only on 15% of the diseases from which people in India die? It is not possible to cover all 100% diseases in the program. Program means resources. So, sociologists can help us by conducting surveys, by talking to people, by doing field work, that from people's perspective, which problems need to be given greater attention. Then sociologists can also help the planners in understanding various dimensions of the problem. Suppose you are trying to solve the problem of why in India maternal mortality rate is high. We know that maternal mortality rate means rate of deaths among women associated with childbirth is particularly high. Sociologists tell them that this problem is not going to be solved simply through health intervention. We have to look at things in entirety or totality, or what we call holistically, and we have to understand that India has a patriarchal system in which in rural areas particularly, value of life of a woman is very little. This is one meaning of patriarchy. So, if you do not care about your women, you will not take them to health center also. There is a problem of transportation. There is a problem of ignorance. People do not know the danger signs. People do not go to ashas. People do not go for ANC. People do not understand the danger signs. There are several danger signs which everybody should be able to know if a woman in the family becomes pregnant. Sociologists tell that apart from health interventions, you require other interventions also: education, empowerment, power of women in decision making, nutrition, control of stress. The sociologists can tell the planners all these. And one important role that sociologists can play in planning process is by involving in monitoring and evaluation of development programs. From time to time, government launches various programs for the benefit of people. Like you all have heard about Manrega, Mahatma Gandhi National Rural Employment Scheme or Act, Manrega, A for Act, S scheme, or other welfare programs. We sociologists can conduct studies and tell to what extent goals of these programs have been attained and what are the bottlenecks or what needs to be done in the future to improve the effectiveness and efficiency. Effectiveness means reach, efficiency means uh, uh, cost benefit ratio, how to improve effectiveness and efficiency of the program. And are there some specific groups where some specific intervention is to be launched to make these programs successful? Something which can work in Delhi may not work in remote tribal areas of Chhattisgarh. So, sociologists help the planners in evolving area specific approach to implementation of their development programs. These days, an interesting branch of sociology called reflexive sociology uh, can also help the planners in understanding if the methods that they are using to solve the existing problems, they are themselves going to create new kinds of problems in the future. Reflexive sociology is about understanding the ill consequences of interventions launched by the government or NGOs or by civil society in the interest of society. Something which we do for improvement or in the interest of society can also create problems. Bureaucracy, for example, created the problem of red tapeism, and health programs led to population crisis. Urbanization led to alienation, and uh, development produced the environmental problem. So, reflexive sociology can help you in anticipating if your solutions are going to create new problems and how to deal with them. Thank you.
Hello, good morning, everybody. I am Raghunandan Sengupta. So I'll just give you a very brief excitement area of finance, which is quantitative finance, and that has a huge market starting around about 10 years back, and it is exploding exponentially. So, what do we mean by quantitative finance? Quantitative finance is actually the application of different mathematical and statistical techniques in the area of financial markets, be it, say, for example, derivative pricing, be it in the area of, say, for example, portfolio management, be it in the area of asset liability management, be it in the area of portfolio management. We see that the application has exploded in such a way that there is a huge opportunity for people who have a quantitative background in mathematics and statistics. They can utilize those in the area of finance, but obviously with some prior knowledge of finance as a subject. Now, when we say about quantitative finance, as I said, it is an area of applied mathematics and statistics applied in financial markets. Use of different areas, if somebody is interested to know, we have stochastic calculus, we have derivative pricing, we have operation research, we have quantitative techniques like differential equations, stochastic calculus, time series, and they are heavily used in the area of quantitative finance, as I mentioned. Now, we all know that in 1997, the Nobel Prize in Economics, so it is basically the Nobel Memorial Prize in Economics, was given to the work of Merton and Scholz in the area of derivative pricing, and after that there has been exponential increase in the area of quantitative techniques in quantitative finance and in the area of different type of derivative pricing. With the advent, moreover with the advent of high-ended and sophisticated computing data, big data has come in a very big way, where application areas starting from computing, from different type of algorithm design have been taken up in such a big way that nowadays at least we are able to understand that how high frequency data algorithm trading can be utilized using the concept of quantitative finance in the area of finance as such. But there is a flip side also, obviously when there is a huge amount of development, so obviously due to some regulation errors or something, there has been some pitfalls, which I think is should be a bullet point for people who are really interested to take up quantitative finance. They should be aware. So consider the financial crisis in 2008 and later on, and we are seeing different banks are failing, different financial institutions are facing a problem, countries are facing a problem like in Europe, in USA. So what should be done? So the main thing is that even if you know the technique is best for people who are investors, who are private players, organizations like banks, governments should use these techniques in a very somber manner such that the application areas of quantitative finance using the techniques which we learned can be utilized in the best possible way to garner the overall the in-depth knowledge a person has in trying to utilize these quantitative techniques in finance. And I am sure that people who have the background, who have the knowledge, who have the sophistication, who have the knowledge of the society can definitely use quantitative finance in a very big way in trying to make their mark in this exciting field, which you are going to see in years to come. And I am sure it will be a very exciting learning tool for all the participants who will take quantitative finance as a subject in years to come. Thank you, and I wish all the participants all the best and best of luck for the programs they will take. Thank you.